In this video, we're going to look at higher order derivatives. So, looking at some of this stuff. So the original function we'll usually see in either sort of a y equals or an f of x type of format. And this tells us the coordinates, the points that we're actually on. F of x greater than 0 means we are above the x-axis, because that's a both way. So above x-axis. F of x equals 0 means that we are on the x-axis. And f of x less than 0 means that we are below the x-axis. The first derivative, let me switch some colors so it can be pretty. In here, we would write usually as dy dx or f prime of x. And this tells us the instantaneous slope. And f prime of x being positive means that the function will be sloping upward, increasing. F prime of x equaling 0 will mean that it is horizontal, as a horizontal tangent at that point, which eventually will end up giving us a lot of times maxima or minima, some of our extrema. And the derivative being less than 0 will mean that it is decreasing, the function is decreasing. But now, a new one, the second derivative. First off, notation. So in here, I can do d squared y dx squared. And a lot of people wonder, why don't you do dy squared dx squared? Well, it's like taking the derivative with respect to x of dy dx. And they're not multiplied together, but notationally you see that I have two d's and two dx's. So that's why d squared dx squared, but there's only one y. I don't have the squared on there. Again, not really multiplication, but that's why that terminology is used, that notation is used. And I can have that as f double prime of x. Now this deals with something called concavity. So before we go any further, let's stop, flip to a different slide, and talk about concavity. So concavity is a way to describe how a function is curved. And for this, if I want to say it is concave up, that's going to mean that the second derivative, or d squared y dx squared, is positive. And concave up basically means that the slope of the slope, the second derivative, so slope of the slope is positive. Or the first derivative is increasing. And how that can happen is this. It can be increasing like this, curving up like that. I could have it increasing like this. I could have it increasing like this. The important part is it's sort of cupped upwards. And you can see, so over here, the slope is positive, but as I move further right, the slope gets steeper, so more positive. In this example, the slope started off as negative, moved towards 0 and then to positive, so it's increasing. The slope is increasing. F double prime is greater than 0. In this case, I started on the left side with a very steep negative slope, a very negative instantaneous slope, and as I move further right, it gets less steep, so the negative number is increasing. It's getting closer to 0 in this case. The opposite of this is concave down. And I've heard my students say like concaving down. No, it's concave up, concave down. This occurs when the second derivative is less than 0. And again, it can occur multiple ways. It can occur during a monotonically decreasing or consistently decreasing function. So it's cupping downwards now. It can occur from a function that changes from increasing to decreasing. This is concave down. Or it can change from a function that's always increasing. All of these, again, these are 3 separate examples, are examples of where a function is concave down. And you can see in this case, the slope of the slope is negative. The first derivative is decreasing, so I started with almost horizontal, almost a 0 slope, but got more and more negative. Or I start with a positive slope and go to a negative slope. Or I start with a positive slope and go to a less positive slope. Now, if you have trouble seeing it, so you can always use a tangent line to see. So if the curve is above the tangent, then it's concave up. And you can see an example here. If I were to draw the tangent line right here, I actually draw a better tangent line than that. That was a terrible tangent line. You can see the curve is always above this tangent line except at this point. And if it curves back around here, I don't care if it crosses later, but around this point I'm above the tangent, so it's concave up. And the exact opposite, if the curve is below the tangent, then it's concave down. And so if I drew a tangent line here, you can see the curve is consistently below the tangent. It's concave down. Last sort of aside here, an inflection point is where concavity changes. So something like this, where I start concave up and then go to concave down, sort of from a sine curve. The inflection point is going to be right here, where it switches from cupping upwards to cupping downwards. And now this is not always the case, but it's often, for our purposes of like tests in the AP test, where the second derivative is equal to 0. I'm going to put a little asterisk on this. I mean often. So I can give examples where the second derivative equals 0, but it's not an inflection point. For example, f of x equals x to the 4th. The second derivative is 0 at 0, but it's concave up everywhere. I can also give examples that have an inflection point, but never get the second derivative equal to 0. In that case, I actually would have an undefined second derivative at a point. And I can do that with a piecewise function, sort of toss together 2 half parabolas, and it never actually gets a 0 here, but it does have an inflection point, because inflection points are all about where it changes concavity. But for our purposes, this often happens where the second derivative equals 0. If people have a ton of questions about finding inflection points, I can make another video that's just solely devoted to these. Okay, back to this stuff. So we talked about concavity. Second derivative tells me about concavity. Third derivative, which we will notate either d3y dx cubed. Now for this, putting a whole bunch of primes next to each other eventually gets very old, so we're going to switch to this notation here. F with a 3 inside parentheses of x, and that's going to be the third derivative. I have seen some people notate third derivative with a triple prime, but this is the point where I usually switch over to numbers, because I'm not going to do like the 10th derivative as f, I don't know, what the deca prime. Now this has a term for it. It's called the jerk of the function, and we'll get into this stuff more later, but for most of our purposes for calculus, for AP calculus, the function first and second derivative are usually good enough, for the questions at least. And then the nth derivative is just taking the derivative n times, and so that would be d to the n y dx to the n, or f nth derivative evaluated at x. So this is notationally how all of this stuff works. Alright, let's see a couple of examples. Here's the first one, which is actually trickier than it looks. So I want to find the first, second, and third derivatives of g of x. So g prime of x, I have to do chain rule. The outer function is sine, so the derivative of sine is cosine. The inner function is x squared. Sorry, I should have left that unchanged. And I need to multiply this by the derivative of x squared, which is 2x. And I prefer writing the constant coefficients and variables before any trig functions. It's just my preference. It's not wrong per se. I haven't seen anyone say that it has to be done this way, but I oftentimes do it this way. And here's where things get a little more fun. So now I want to take the second derivative. But I have something going on here. So I have 2x cosine x squared. First thing I'm going to do is I'm going to take this 2, it's a constant multiple, I'll just bring it down. But now I have x times cosine of x squared, and that's a product rule with a chain rule part. So I'm going to go through and do that. So product rule is the outer thing I need to take care of. And so I will do g times f prime. So I leave the second part unchanged. So cosine, cosine of x squared times the derivative of the first function times 1 plus the first function, x, times the derivative of the second function, which is going to be negative sine of x squared times 2x. Okay, let me make sure I have the correct number of parentheses. All right. And so let me clean this up a little bit. So I'll distribute the 2 through and combine some like terms, and I'll get 2 cosine of x squared plus the 2 times this 2 gives me 4, but I guess I should have a minus because of this negative sign, minus 4 x times x gives me x squared sine of x squared. And as you can see, this isn't too bad, but this is kind of ugly now. So when I'm going to the third derivative, I have to deal with this mess. And it's not terrible, so this part, well, 2 is constant multiple, so bring down the 2. And the derivative of cosine of x squared is chain rule. Take the derivative of the outer function, I get negative sine of x squared times the derivative of the inner function, which is 2x. And that's easy enough to clean up. But now I have this mess, so I'll start off the same way, minus 4, and I have product rule with a chain rule. So I do this times the derivative of that, so I have sine of x squared times 2x plus that times the derivative of this, which is going to be x squared cosine x squared times 2x. And now I just need to clean this up. So 2 times 2 is 4 with a negative sign. Negative 4x sine of x squared. And in here, I'll distribute the negative 4 through to all of these. And so I'll have negative 4 times 2x, so I have minus 8x sine of x squared. And multiply this through to these, so I get negative 4 times 2 gives me minus 8. I have x squared times x, which is going to be x cubed cosine of x squared. And one more thing, I can combine these like terms. I will get negative 12x sine of x squared minus 8x cubed cosine of x squared. As you can see, a ton of fun with these. From something that started off as a very simple function. Alright, one more example. So in here I want to describe this graph around x equals negative 2 and refer to the value first and second derivative. So what I'm going to do is this. I'll first evaluate y of negative 2, which is going to equal 4 times negative 2 to the fifth minus 5 times negative 2 squared plus 2 times negative 2 minus 3. Negative 2 to the fifth is 32 times 4 is 128, but negative, so I have minus 128. Negative 2 squared is 4 times negative 5 is minus 20. 2 times negative 2 is minus 4, minus 3. So let's see. Negative 128, negative 148, negative 152, negative 155. And I'll put to the side what this tells us once I go through all this stuff. Alright, next thing I need is y prime. So y prime of x is going to give me 20x to the fourth minus 10x plus 2. And I need to evaluate this at negative 2 to see what's happening there. So 20 times negative 2 to the fourth minus 10 times negative 2 plus 2. Negative 2 to the fourth is 16 times 20 is going to give me 320. Negative 10 times negative 2 is positive 20 plus 2, and that gives me 342. And I continue, again I'll write to the side what this tells me shortly, with the second derivative. Let me not go to negative 2 yet, let me just do it of x first. So the second derivative of this, while I bring the 4 out, I get 80 x cubed minus 10. And so I do the second derivative, evaluate at negative 2. 80 times negative 2 cubed minus 10. Negative 2 cubed is negative 8 times 80 is negative 640 minus 10, which gives me negative 650. Now what does this tell us? Okay, this means that we go through the point negative 2, negative 155. The derivative tells me that we have instantaneous slope of 342. Now, for the AP, they love these two words, increasing, decreasing. They're going to want you to say that if you have this type of problem. So I could write this as, let me put it in quotes, increasing at a rate of 342. And this right here, being negative, tells me that it is concave down. So, lovely, that's what it tells us. Let's look at the graph and see if it actually goes through this point with that incredibly positive slope and is concave down. So in here, here's the graph, and I need to get to negative 2, negative 155. Okay, just scrolling. And, alright, there we have it. Let me actually plot the point. Negative 2, negative 155. And hey, there it is. And we can clearly see, yes, it is incredibly steep here. It's increasing very quickly, so that 342 seems to make sense. The last part, it's a little bit hard to see the concavity here. So I'm going to actually stretch this a little bit to help us see. So let me zoom out, go back up to here, and stretch this in until you can see that, yes, in fact, this is curving down at this point. Okay, it's by shrinking it so much, you miss just how much it's curving down, but it is curving down. All right, feel free to comment below if you have any questions.